Today is the first time for the online teaching because of the situation of COVID-19, okay? But I think we all get used to the online teaching and online learning already. So you still can send me email when you have problem and questions about this subject, okay? And for the last lecture, we mainly discuss about the definition and the calculation for the simplified hypothesis B method. Okay, I I know some of you might have some difficulties in understanding the procedure of calculation and the definition, as well as the concept. Okay, I prepare to re-elaborate more in today's lecture. Okay, in this afternoon, and for today's tutorial, I may go through with you the example 5 to example 8. Okay, so actually because the name, okay, the simplified method, okay, for the calculation process, it should not be complicated. It's very easy to master the procedure of calculation because all the equations for different conditions, for different cases, have been well presented clearly, okay, in the slides already. So after you practice with the examples, for example, example 5 to example 10, okay, especially example 10, if you know the details and the meaning behind the calculation process, I think it will be easier for you to understand the concept, okay? So for calculations should not be very challenging for all of you, but I hope you can understand the reason, okay, why we can do this kind of assumption. We should do this kind of simplification, okay? The reason behind. So let's go through the example first today. And before the examples, I want to discuss with you again the so-called three methods, okay? The three methods here. And this one, hypothesis A method, we learned it in the solid mechanics, okay? The main difference between hypothesis A method and hypothesis B method is very important for you, okay, to know the main difference between these two. So the main difference is that hypothesis A method assumes the creep only occur after 98% saturation degree has been achieved. However, hypothesis B assumes that creep is only related to the effective stress. That means when you have effective stress on the soil, we have creep. No matter the excess pore water pressure has been 98% or 100% dissipated, okay, no matter. So this is hypothesis B, this is hypothesis A, okay, this is the difference between both of them. So for hypothesis A, we have two items. The first item is the average degree of consolidation multiply the final strain or final settlement, okay? This final settlement is easy to calculate, okay? We have two methods. For SF, we have two methods. One is MV multiply delta sigma prime, then multiply the thickness, right? If we know MV, we know the change of the effective stress. This is the thickness of the soil layer. Another method is from using this graph, log sigma prime and E or epsilon, okay? Both of them are okay. We use this graph if we have the slope of this elastic part, or we call it unloading, reloading part. We also have the slope of this normal consolidation line, okay, NCL line. So if we have two slopes, we can also get the result for the final settlement. Okay, we have two methods. Normally, we prefer to use this method. Okay, this is a more comprehensive method. We can know more information about the soil behavior. Okay, so for the UV, we can calculate from T to TV and get UV if only 1D drainage occur. Okay, if there is a vertical drain installed, we should consider the UR also, right? And then use this equation. Then use this equation to get the average consolidation degree in the hole, okay? Then to calculate this UV. So if we have vertical drain installed, actually, we should not have this V, because this V means vertical, right? If we have the UR value here, this UV should be replaced by U, okay? U multiply SF plus S script D, okay? So this is a first item for the hypothesis A method. And the second one is the script D, or the so-called secondary consolidation or secondary compression, okay? This only happens after 98% consolidation has been achieved. Okay, this is hypothesis A. So we say hypothesis A method underestimate the settlement. Why? Because it doesn't include the settlement due to creep during primary consolidation, right? That's why it will underestimate. And for the hypothesis B method, the older one is the first one, okay? Alpha is equal to 1. Alpha equal to 1. This part is equal to 0, right? So for the old one, S creep final is the final creep settlement without excess pore water pressure UE coupling. Okay, as I discussed with you in last lecture, the so-called without excess pore water pressure coupling, you can understand in this way. Okay, the effective stress is immediately increased to its target value. Okay, we have a delta value here. This delta value for the soil element instantly or immediately increased. Okay, we don't have to wait for a long time for the UE to dissipate. Okay, to dissipate. So this is not the truth, right? This is not the truth. That's the reason why the old simplified hypothesis B method will overestimate the settlement. Okay, this is the reason. So we know the limitation of these two methods. In several years ago, around 2017, Professor Yin and his student, okay, proposed this new method. We use alpha is equal to 0.8. 0.8, this value actually is from, we obtained from the a lot of experimental tests, okay? We found that alpha equal to 0.8 is most suitable, okay? Most suitable value for get the reasonable result. So alpha equal to 0 here, we combine both of them, the older one and hypothesis A method, okay? And as I discussed with you, this one is a correction for the thickness of the soil layer. Okay. Hope this will help you to understand better, okay? Because if the soil thickness is very small, it will be very quick to achieve 98% overall consolidation degree, so that we will have a large secondary or large creep with the time passing by. Because 98% can be very easily achieved or very quickly achieved for a very thin soil layer. That's why we should include this item here. But if for a very thickness of the soil, 98% take a lot of time for to achieve, right? That's why if this soil is very thick, actually this item will be very small, okay? Will be very small. So this is the reason why we have the current new simplified hypothesis B method here, okay? But actually they are should be not very complicated to do the calculation, okay? Let's see from today's example. Here is example 5. Okay, we have 3 minutes for you to go through the question first. Okay, let's see this question. And the thickness of one layer of Hong Kong marine clay is 4 meters, okay, with bottom impermeable and top free drainage in 1D straining. 1D straining actually just means 1D compression, okay, 1D condition. The over consolidation ratio is 1 and 1.5. Okay, we have 2 cases actually. Here, uniform pressure due to sand fill is applied suddenly. okay, suddenly. We assume it applies suddenly. We don't have to do the correction for the construction period. And the stress level is 20 kPa. The saturated unit weight of the clay is 15. And other parameters are given in this table, and calculate the average strain, MV, CV, and final settlement SF. Okay, by dividing layer into different layer numbers and discuss the difference. Okay, and we are going to calculate MV, CV, final settlement SF, and average strain. Okay, if we know the average strain, we can get the SF, right? Because we know the thickness. And with the deformation or the strain value, we also know the effective stress change. We can back calculate the MV value, right? With the MV value, we know the CV is equal to K MV gamma W, right? So from MV, we get CV. So this is the logic, okay, for this question. And the CE, CC, C alpha E are all given here. Kappa, lambda, per psi, okay, as I discussed with you, the kappa lambda per psi actually is another expression, okay, another format or symbol, okay, to represent the elastic compression index. This is the slope, right? This is related to the creep rate, C alpha E, okay? So this three is just for your information, okay? Another symbol, but we prefer to use a more commonly used symbol, CECC and C alpha E. And the V specific volume, T0, okay? T0 is always equal to 1 day. And the KV, the permeability in the vertical direction, is given here. Okay, M is meter per day, okay, per day. Sometimes we will use meter per second, okay. If it's meter per second, this value will be in the amplitude or in the order of 10 minus 10 to 10 minus 8, okay. For Hong Kong marine deposit, normally this is the range, meter per second, okay. So let's see the calculation process. Okay, here shows you the sketch of this soil layer, okay? And we know the slope. See here, we know the slope of the CC here, right? So let's move to the Excel file. Okay, I think you can see my Excel now, right? Okay, so for the first case, the OCR here is equal to 1. OCR here is equal to 1. So, which means the settlement, okay, happen or occur along the NCL line, along the NCL line. So you can see that here, the initial vertical stress is equal to 10.38. We just use this initial one, okay, and the final one is 30.38 because the data change of the effective stress is 20 kPa, okay? For example, 10 is here, 30.38 is here. So all of them are happen or are located at the NCL line here, okay? So the only slope we need is the CC value, here, which has already been given. So you can see the strain, okay, we directly calculate this E, okay, here you can see this is a E. Actually, it's optional, okay, it's optional. It's optional. So the strain can be calculated. The final stress is here, final stress D0, the the cell of D10, and the initial value is here, okay? Here, CC MV, okay? Just use that very simple equation, okay? We have it on the slide. And the thing I want to discuss more is about when the layer thickness is 4 meters. The mid sublayer depth is 2. Okay, so that means we use stress change of the middle point of this soil layer to represent the average stress change of the whole layer. Okay, so if you divide it the soil layer into 2 layers, so we have 2 mid sublayer depths. For each layer, we calculate the initial vertical stress and the final stress. Okay, so similarly, if the soil layer is divided into 8 layers, actually, we just do the same thing. Okay, the only difference is the determination of the initial and final effective stress. Okay, the formula are all the same. So with total strain here, we can get the MV value, right? Because we know the change of the effective stress is 20. So MV value can be easily determined. Then from MV, we can calculate the CV, okay, as we discussed. So you can see with the increase of the number of layer, we divide this soil layer. Okay, you can see that the strain become larger at the beginning, okay, then become stable, okay? That means with the increase of the number we divide, the accuracy will be increased. Then if the number or the average, the thickness of each layer is around 0.5 or 1 meter, okay? So the accuracy becomes more acceptable, okay? Because the settlement or the result becomes almost stable, okay? No need to do further division, okay? Then for the OCR equal to 1.5 condition here, 1.5 condition, that means the initial point of the soil element is on this line, the OCL line, okay, over consolidation line. Then let's see the final point. Where is the final point? Okay, how to determine where is the final point? We should compare. We should compare what? We should compare. This is a pre-consolidation stress point here, because we need to determine, okay, after 20 kPa increase of the effective stress, we should determine the final point is here or here. Okay, if it's this point, we only use CE is good enough, because from here to here, okay, all of them locate on the OCL. But if it locates on the NCL line here, so we should have the CE and CC, okay? So let's see. The initial point, the initial vertical stress is 10.38 again, okay? After 20 kPa is applied, the total final stress is 30.38, right? And because the OCR value is 1.5, so the effective pre-consolidation stress is equal to this value multiplied by 1.5. Okay, so we get this value here. We can see that this value is smaller than the final stress. Okay, you can compare all of them. All of them are actually smaller than the final stress. So that means the starting point is here, then we pass by the effective pre-consolidation stress, then come down along with the NCL, okay? So the calculation of the strain a little bit complicated than the OCR equal to 1 case. Okay, so one by one, we get the total strain here, we get the MV again, because we know the effective stress change. Then we further get the CV, okay? This is a process to calculate the S final, okay, S final. Actually, we are talking about the one by one, okay, to divide the so-called simplified beam method into different sections, okay, to teach you how to calculate each of them. Okay, this is the simplified beam method, right? B. So now we all know how to calculate SF already, okay? Let's move on. Okay, we go back to the PowerPoint. Based on example 1, calculate the curves of the settlement versus log time using hypothesis A method first, the old one, B method, okay, and the new simplified B method. For the 4 meter thick layer with OCI equal to 1 and 1.5, using alpha equal to 0.8 for the new method, okay? Discuss the difference of curves. So we only have this condition here. The sublayer thickness is equal to 0.5. So the division number is 8, okay, for these two cases. Let's see, directly go to the Excel file. So we have the different equations for these three methods here, okay? And to calculate the relationship between the settlement versus the time, okay, versus the time. So the first column, you can see here, the unit is day, okay, from 0.1 day to a very large number, okay? This is almost the 300 years here, okay, for the long time prediction. And the same, we just use the example 5 to discuss with you how to get SF. Then we should get the U, right? To get the U first. U here, UV. UV from TE to TV and to UV. One thing I just want to remind you again is the equation for get UV. When UV is smaller than 0.6, we have one equation. When UV is larger than 0.6, we have another equation, okay? So you can see here. This one, we use this equation because U actually is larger than 0.6. But here, actually, we use another one. We use another equation, okay? This is the difference here. Why we use two different equations for getting UV, okay? So with the UV and SF, SF is calculated from the example 5, okay? From example 5. Okay, so we have a constant value because we calculate from last example. And for the old B method, S-script final, how to calculate? First one, in the simplified hypothesis B method, the creep only occur after T0, and T0 is equal to 1 day. So that when T is smaller than 1, we don't have this item. The S-script final are always equal to 0, right? You can see here. Then after T is larger than T0, we finally get the value for S-script final. You can see the equation here. Actually, this one, okay, this equation I have already put it here already. C alpha E divided by the specific volume log, okay, the final time, the initial time, okay? The final time, the initial time, okay? So you can see that here, the equation, the final time is Q7. Why? Because T0 plus TE is equal to T. TE is always equal to T minus T0, okay? This equation always correct, okay? We can discuss more in today's lecture to re-elaborate the concept, okay? So the T here, TE plus T0 is equal to T. This T is the time you apply the loading on top of the soil ground. So the final one, this one is the initial one, okay? Initial one, F4. F4 actually is equal to 1, okay? Always equal to 1. So we use the same equation here to calculate the S creep final. This equation, okay, to calculate. And for the A method, the S creep final only occur, or I cannot say S creep final. The creep only occur after 98% consolidation degree has been achieved. So for this part, we have no creep, okay? We have no creep. We only have creep after 98% has been achieved. Here, you can see. And there are something different. The final time, okay, is the time here, 20,000 days, okay? 20,000 days. But the initial time here is this one, is this value, 14300, okay? Why? Because the creep only occur after this time point. So the creep should be the final time, okay, minus the initial time here, at which 98% consolidation was achieved. So this is the difference to calculate the S creep for the A method, okay, here. And new simplified B method actually combines these two together, okay? So this column in new simplified B method, we can call it S creep D, S creep D, okay? S creep D, because only occur after 98% has been achieved. So this one, for the new method B, is very simple. We just use this equation to have the alpha equal to 0.8 to calculate the result. So we can see here, 0.8 multiply U22 is this one, plus 1 minus 0.8 actually is equal to 0.2, multiply V22, okay? To combine these two items together with different weighting, okay? We can say the alpha is a weighting value, okay? A weighting value, and 1 minus alpha, okay? So this is a new simplified method. And the A method is here, the old one is here, okay? We just use different equations here to calculate. Should be simple, okay? And then use the new method, new hypothesis B method to calculate the final settlement. The final settlement, actually, we should include the settlement due to primary consolidation, right? So you can see what we have more. We use the creep settlement calculated from the hypothesis B method in this column to plus the settlement due to the primary consolidation in this column, okay? We get the final result. Okay, this is how we do the calculation here. And for the OCR is equal to 1.5. Actually, nothing big difference, okay? No big difference. No big difference. Let's compare. Let's compare. Let's compare, okay? So UV is the same from T to TV and to UV. Then multiply the SF, okay? The difference is SF value, okay? The SF value calculated in the example 5 is different, so that the final result will be a difference for the primary consolidation part. And for the B method, old B method for calculating the S creep final, actually they are same. Why? Because the final point are always on the NCL line, okay? The final point are always on the NCL line, so that the equation for calculating the S creep final is always use this one, okay? Always use this one. No need to go to a complicated case for the OCL line condition, okay? Because we do the comparison here, okay? The final point is always on the NCL line, okay? So you can go through by yourself the Excel file. I have already uploaded the Excel file in the Blackboard, okay? You can see very detailed information, okay? The calculation procedure, okay? In this Excel file. So nothing, a big difference, okay, between these two conditions, because the final point are always on the NCL line, okay? The same equation here is used. So this is example 6. And if we plot the result in figure here, you can see that the hypothesis A method is this one. Underestimate, right? Underestimate. And the solid line, this one, is the old simplified method. Overestimate a little bit. Okay, compare with simulation result. Okay, these two simulation result is fully coupled. Okay, fully coupled result. We can believe that the simulation is more close to the real condition. Okay, so we here put these two results as the reference. Okay, reference the triangle marker and the red circle marker here. Okay, you can see. Then if we use the new simplified method, the purple one with red circle, okay, here, this one is the best one, right? Because they are more close to each other. Okay, the red purple one, the red circle with the purple line. Okay, they are more close to each other. So you can see this is the result for the OCR equal to 1 case. And for the OCR equal to 1.5 case, again, this one underestimate, this one overestimate. Then the purple one gives you the most accurate prediction here, right? That's why we always say the new one actually is a better one, okay? Let's move to the example 7. Example 7 actually is a very comprehensive example. It's a very important example for you to go through the calculation process, okay? I hope you can, after today's lecture or tutorial, you can go through by yourself, okay? For 1 or 2 times to understand each procedure, okay? This one is very important. And the soil is with double drainage condition and the thickness is 10 meters, okay? And in 1D streaming. Other parameters are given in this table. Calculate the settlement of different states at loading duration, okay, 5 years, sometimes 100 years, okay, different loading conditions. And from point 1 to point 2, okay, this is the first case, from point 1 to point 2. The load is suddenly applied. No need to do the correction for the construction period. The value is, CV is constant again, okay? CV is constant. And CE is here, CC is here, C alpha E, okay, given already. Specific volume, CV constant for all, okay? For, I mean, during the whole duration of the consolidation, CV is always constant, okay? This is an assumption in Tesaki's theory. And T0 always equal to 1 day, okay? And you can see there are 6 series, okay, six sets of data here. And the first one is for the point 1. Effective stress, the strain value, okay? So if you use these 6 sets of data, actually you can plot the figure here. You can plot the figure here. 1 here, 2 here, maybe 3, 4, 6, 5, okay? So they are all from plot from the real data here, okay? You can plot another one because this one is just for I mean, to showing the position, relative position, okay, but not to scale, okay? Not exactly to scale. So you can plot by yourself to understand the relative relationship between different stress states. Okay, let's move one by one. And if the first case, the loading from point 1 to point 4, point 1 to point 4, okay, starting from the OCL line to NCL line, okay? So starting here, it will surpass this one, this loading, this stress state first. So it will go along OCL line first, then to the NCL line again, okay? So for the calculate S final, we should use CE and CC. My screen is, sorry. My screen is frozen. Or maybe some technical problem, okay? Maybe, so you can see my marker now, right? Is okay now? Sorry, I don't share with PowerPoint with you. Now I think it should be fine now, right? Okay. I just go through the question body, okay, with you. Let's move on, okay, from one by one, okay, the cases. From point 1 to point 4, we will surpass the pre-consolidation stress here. First one CE and the second one CC, we already have. So for calculating the S final, we should have two items. The first item for OCL line, the second item for NCL line, right? No problem. The only thing is we should carefully to determine the final stress state, the initial stress state, the final stress state, the initial stress state on each lines, okay, on each line, so that we can get the accurate result for the S final, the S final. So this is a method using this design, this chart or this figure to calculate S final. Then we should calculate S script final, okay, the second item in the simplified B method. So at the time point of 5 years, the S script final can be calculated using this equation. Why? Because the final stress at here, the point 4, is at the NCL line, right? So we use this equation. And T0 is equal to 1. And TE, how to calculate TE? TE is equal to T minus T0. T is 5 years. 5 years means the loading is applied and kept for 5 years, okay? This is a total loading period. So use the T minus T0, we get TE. Actually, this T0 can be canceled. The only thing remained is this T, okay? You can see here. So we can calculate the S script final using this equation. And for calculating the UV, okay, we actually discuss a lot of time because this soil layer is double drainage. The water can go out from the top boundary and can go out from the bottom boundary, okay? So the D value, the longest drainage path is equal to 10, the thickness divided by 2, which is equal to 5 meters. And the TV use this equation, no problem, right? And the UV use this equation, no problem. You can try to use this equation to get UV first, which is smaller than 0.6, which means you use the correct equation, okay? If you calculate using this equation and get the UV, which is larger than 0.6, okay, then you need to do the calculation again to use this equation, okay? To use this equation to get a UV here, okay? We try first, okay? And then to determine on whether or not you use the correct equation, okay? And S script D is equal to 0 because the UV is much smaller than 0.98, right? So the total one, this item equal to 0, okay? Ignore it. And S script final, we calculate here, multiply the alpha equal to 0.8, okay? Plus the settlement during the primary consolidation, we get the final result. This result means the final settlement at the time point of 5 years. Okay, this is the result. So this is the first case, a simple one. Okay, let's move to the second case. The loading from point 1 to point 2. Point 1 to point 2. Point 2 is locate on the OCL line. So it reminds us something different. Okay, as final, we only use the CE is good enough. Okay, no need to CC. So we calculate the final result using the final stress state and the initial stress state, right? And TE2, okay, TE2. This equation has been given in the slides, okay? We can see the parameters one by one. Epsilon Z2 already be given in the question. Epsilon ZP, the pre-consolidation stress, the strain, okay, the strain at the pre-consolidation stress state here. And specific volume C alpha E, the effective stress state for point 2, pre-consolidation stress CC C alpha E T0, okay? We have all the parameters, the values for all the parameters here already. So we just put it inside and calculate. A very large day, okay, a very large. By the way, you can see here, the TE, the equivalent time for point 2 means the time needed for reaching point 2 by creep from the reference timeline. Okay, this is the definition of the equivalent time. So you can see here, if the starting point to reach point 2 is at 2 prime, point 2 prime, okay, here, by creep, slowly creep to this point, point 2. Actually, it takes more than 10,000 days to reach point 2, okay? A long time. Okay, a long time. So at the time point, which is equal to 5 years, we use this equation. Why? Because the point 2 locates on the OCL line here, OCL line, rather than the NCL line, okay? This is the point 2. So we use this equation, T, 5 years, the total loading period, okay? T2 we get it already, T2 we get already, and T0 equal to 1, okay? We put all the data downwards to this equation, we get the S-curve final here. So again, UV is equal to 0.526, okay? The similar, okay? Same result as the last case. Then we put all the data into this simplified B method equation, we get the final result, okay? The only difference is the point 2 is on the OCL line, okay? And here we use a duration of 100 years, okay? A larger duration. Let's see what happened here. The final one never changed because everything is fixed. The final one, okay? The final one. The TE is the same. At the 100 years, S-curve final, this T will become larger, okay? In last case, this T is 5 years, now 100 years. T2, no change. T2, no change. T0 always equal to 1, right? So this value we can get. The only thing change is here. The UV actually now you calculate by yourself, you can check. This one is larger than 0.98. So the final settlement, okay, becomes larger, of course. One more thing, discuss more, okay? Here, this equation, because this U is larger than 0.96, this equation, okay, is here, this one. We no longer use this one, okay, because U has already exceed 0.6, okay? So this is the difference with the last case. So let's see. And 100 years S-curve final, okay, now we should calculate the S-curve D. We should calculate S-curve D because U larger than 0.98, okay? So as for S-curve D, we discussed this equation here last time already. T we know, TE2 we know, TE2 we know. And for the TEOP at the field, for this value at field, let's see how to determine this one. At TEOP at field, which means the U is exactly equal to 0.98, right? So this is a back calculation process. We know U to get TV, then we get TEOP at field. Okay, you can use the lowercase for the time. Okay, this is time factor. So you can see the procedure is shown here. U we know get TV, then from TV we get T. Okay, this T is more than 76 years. Okay, so we can use this value here, then get the S-script delay. Okay, S-script delay. Then we put it here. Okay, so when duration becomes larger, okay, larger enough, U larger than 0.98, we should do something different. Okay, one is to calculate UV, the equation for calculate UV. Another one, we should increase S-script delay. Okay, these are two different aspects. We should pay more attention when U is larger than 0.98. Okay, and again, there is another new case, unloading case from 0.4 to 0.6. Okay, so you can see that CE we know the final one is here, 6 one. The initial one actually is a larger, is a larger value. Okay, it's a larger value, initial one, so that we get a minus or negative value here. SF is a negative because this is a unloading process. We release the top loading, which means the soil will bounce back. Right? Will bounce back. So that the SF will be a negative value. Settlement becomes smaller. Okay. And TE6, okay, I don't repeat here because TE6 is locating on the OCL line. So the equation is the same as the condition for 0.2, okay? So TE6, we have T here. We just put down the value here. T is equal to 5 years. You can see this value is very, very large value because you can see if we draw back further, okay, the NCL line. Okay, so the length of this, okay, of this section is much larger, okay, than the length of here. So this is the reason why this value is so large, okay, because it takes a longer time to reach 0.6 by creep from the reference timeline. Okay, so this value is quite large. And UV again is equal to this value because 5 years doesn't change. Okay, finally we get this result. It's minus, okay, it's a negative value because this one is negative. Okay, so again, I want to say a little bit more with you. You can see if we have a pre-consolidation stress here at 0.4, then we bounce back to 0.6. You see, we bounce back to 0.6. This is preloading, right? What we discussed in the lecture, preloading process. Okay, preloading. Then you will see that the creep strain or creep settlement is almost equal to 0. Okay, it's very, very small value. This one is equal to 0, but this one is almost equal to 0. Okay, this is why we will normally adopt the preloading method, also called surcharge or even vacuum preloading method. Okay, to reduce the post-construction settlement. Okay, you can see the calculation here very clearly why we do adopt this kind of method. Preloading from 0.6 to 0.5 here. Okay, this should be no problem. The final one, the initial one, the TE5, we use the same equation. T here to get the S-script final, use this equation, okay, on the OCL line, so that we use this equation. And UV, again, is this value because 5 years, okay, 5 years. Again, we have this result, okay? I think it should be okay for you. S-script D is equal to 0. And for the example 8, calculate the curves for the settlement and the time for the case of loading and final strength state. Okay, you can refer to the Excel file I uploaded in the Blackboard. Okay, in the Blackboard. Actually, the only difference actually is a repetition. Okay, repetition, just a repetition of this case, 0.1 to 0.64. Just a repetition of all the procedure here for different time points. Okay, here we use 5 years. Here we use 5 years. Okay, we just add 10, 20, 30 until 200 years or something. Okay, for produce this table here and get the figure. Okay, here. So this is all the 4 examples here I discussed with you. Okay, today's tutorial, okay, for the first hour, this is all I want to discuss with you. Do you have any questions? Okay, do you have any questions about the examples today? Okay, again, I want to mention, okay, mention again about the so-called simplified method, okay? Actually, it's really simplified for you to do the calculation. So the only thing is to understand the reason and the concept behind, okay? To know more, okay, about this method. So the calculation should be okay. In the future, next week, we will discuss the example 10, okay? I hope you go through with me carefully about the example 10, okay? So if you have no question, I may take a break, okay? Maybe some student will join for the session 2, okay? I may come back 8 minutes later, okay? 8 minutes later. By the way, I will only record. For the first session, okay? For the first session, because for the second session, almost everything will be repeated. So I don't think I have to record again, okay? So I will stop recording now.
Recording stopped.
You can go to Blackboard to review again, okay, if you want.